Yeah. Okay, so let's go. So, hello everybody. My name is Eric Blayo. I'm a professor in applied mathematics here in Université Grenoble Alpes. So I will be the honor to be the president of your jury, Sofya, for your PhD defense. So this PhD was advised by Bruno Raffin, who is a senior scientist here at INRIA, Grenoble. And we have two referees who are Ronan Fablet at IMT Atlantic Institut Mines Telecom in Brest, and Mathias Niepert, who is a professor at the University of Stuttgart. We have also an examiner who is Cranmer at the University of Wisconsin-Madison. That's why we are so late in the afternoon, the time lag. And so it's up to you now for your presentation, let's say 45 or 50 minutes, and then we will ask you some questions.
Thank you. Well, hello and welcome everyone. Thank you for coming and thank you for joining online. I'm very happy to finally present what I was working on these years during my PhD. Scientific computing drives discovery and progress in science and engineering. It allows us to study real-world systems and phenomena that are too expensive, too slow, or simply impossible to observe or experiment with. By describing the system in mathematical model, we're able to represent the system on a computer and using the algorithm called solver, produce the simulation of the system behavior, which then can be analyzed. While running the solver algorithm is considerably cheaper and faster than actual experiments, its cost still can be pretty high computationally for some tasks, requiring thousands of computers running for weeks or for days or even weeks. Therefore, reducing the cost of obtaining simulation data is the major goal of the field. There are traditional methods that are producing the simulation data faster, but at a cost of accuracy. With the rise of AI, we are offered a new alternative solution, deep learning-based surrogate models. Those are neural networks that are trained to predict the system behavior, and then they can be used to predict the simulation, the system behavior as a simulation data, fast and relatively accurate. And they can also be used even for tasks that are beyond the capabilities of a solver, which usually would require some auxiliary methods. However, the success of these methods depends on how well they are trained. So let's take a look at how do you train a neural network. In deep learning, standard practices are developed for tasks where you are given the observational data. So here, for example, we have a data set D of size n, which then is given to the neural network, the model F with the parameterized by the weights theta. These weights are optimized by minimizing the error between the neural network's prediction and the data ground truth answers. Then the neural network can generalize to unseen data. In our case, for scientific computing, however, we're not given the observational data. We work with synthetic data, so the one which is coming from the mathematical model, PDE's equations, and the solver. So we need to create our own training data. You would have a parameter space, a continuous space distribution of lambda. Then you need to sample endpoints from this space and create your training data. To improve the training of surrogates, we could focus on improving just the model itself or the training algorithm. Or since we do have this ability to create our own training data, we can focus on this, how to create the training data that is more useful for the neural network to train. So this ability comes with a question, however, which data we need to create to train well. Let me give you a simple analogy. Imagine I'm a math teacher and I have a student which I need to prepare for the exam on multiplication. So I need to prepare the practice exercises by choosing parameters A and B. As I have no information, prior information about the student's knowledge and failures, I can just sample a lot of A and B uniformly. Give these practice exercises to the student to practice until the exam. However, at the exam, they will fail because they didn't spend enough time practicing harder exercises like multiplying by 6 or 7. Because they spend a lot of their time for practice multiplying by 1 and 2. Or I could apply an active learning approach. In this case, I would create a set of exercises, then give it to the students, see which exercises are harder or easier for them, and prepare the next set of exercises accordingly. This way, the practice will contain only useful examples for the student, and they will succeed at the exam. The same active learning method is well established in deep learning, but however, again, for tasks with observational data. You would be given a set of data without labels, a lot of data which you wouldn't be able to label for neural network training data sets in short time. So you would want to select which data need to be labeled. You would apply pool-based active learning methods, pool because you have a pool of data. In our case, we can also try to apply the same methods. But since we don't have the set of data given, we have the parameter space, continuous space, we can just sample a lot of points to create our own pool and then apply the pool-based methods. However, there is a problem that it can be insufficient to cover and represent the continuous space with a discrete set of parameters. Or you would need a lot of points to do so, and then you will spend a lot of time applying the pool-based methods to select, to iterate over this pool. There is another family of active learning methods called query synthesis active learning. In this case, you don't have a pool of data, you're synthesizing directly the data which needs to be either labeled or in this case, created. It is not so well established in observational-based tasks because it's not so easy to synthesize a realistic image of a cat which would really come from the distribution of the data. In our case, however, we can do that. It fits very well. So how can we apply query synthesis active learning? This brings us to my first contribution method, BRID. Let's take a look at this simple dynamical system, toy example. You have a ball placed somewhere at the starting position, somewhere on the surface. Then you have a black box oracle, which would provide you the outcome of the system where the ball rolls on this surface. So the final position of the ball, in this case, one of these two bits. The task is to train the neural network to mimic this behavior to predict the outcome of the ball rolling from some specific starting position. So to train the neural network, we will need to create our data. Here we would choose the prior distribution over the parameter space of starting initial positions, then sample endpoints from this prior, and obtain the outputs, the ground truth outcomes with the oracle. But how to know which samples are useful or not? In this case, when you're looking at the surface, it can be easy to guess that a lot of starting positions, the outcome will be going directly into one bit or another. But there is this region of starting positions on the border between the two of them, where you will be uncertain about the outcome. So if you see more of these examples, and so the neural network will see more of this training data, it will be less uncertain of it, and it will be more useful data for training. So how can we get this prior to be proportional to the uncertainty distribution? It comes with some challenges. First of all, the uncertainty doesn't have any closed form as a distribution, meaning that we can't sample from it easily. Instead, we can approximate it with a weighted density estimator, which is evaluated at some specific points to get the uncertainty values, and then approximate. Second, the uncertainty estimates can be very costly. So instead, we can use a cheaper proxy, neural network loss. And then we have the neural network, which evolves as it's training. And so does the neural network loss and uncertainty about the data. So we can't just fix our prior of the distribution. We need to update it in some kind of rounds to follow the neural network evolution. However, these rounds of updating the dataset can incur some distributional shifts in the data, which can destabilize the training of the neural network. So instead of changing the prior too drastically, we can try to adapt every round of new data based on the previous one to generate samples which are more or less close to the previous ones. And last, since the neural network loss affects the prior, and so the prior then affects the neural network loss, etc., you can have this is a closed loop which can incur mode collapse, the overfitting on these specific points, which are the hardest, and underexplore the space in general. So we can mix our prior with a uniform distribution to maintain the exploration of the space in general. So how does my method BREED achieve these ideas, achieve these solutions? First, we initialize a data set S of n samples sampled uniformly in the space. Then we train the neural network for P iterations, so where P is a hyperparameter which controls how fast do we adapt to the neural network evolution. Then we compute the loss for each of these samples, and accordingly we build the proposal distribution, which is a mixture of Gaussians, weighted accordingly to the loss values at the points. Here we have a hyperparameter sigma, the width of the Gaussian kernel, which controls the diversity, so how much the next round of data is different from the previous one or more concentrated. Then we create a mix of this proposal with the uniform, controlled by the weight and weight alpha, to understand, to have a trade-off between exploration and exploitation of our prior. And then accordingly, we sample some points from our Gaussian mixture, others from the uniform, and we have our final data set for the next round, and we repeat this process. So does it work? We applied BREED for this before-mentioned dynamical system with a ball on the surface. I created two validation sets. First one, where the points are sampled uniformly across the whole domain. And another one, it's a region of interest validation set with points where the surface has near zero gradient. So exactly this area which we determined to be hard, uncertain, because one little movement of the starting position and it will be either one or another pit where the ball falls. On the left, you can see the test loss progression over training for both of the validation sets. We can see that BREED in blue makes the neural network converge earlier and to lower values. As well, you can notice that the values of the loss for different validation sets differ by almost a magnitude, which makes a very important point about looking at the validation set. As we can create the training data, we can also create our validation set. So we need to be very accurate about it as well. And on the right, you can see the test loss distribution over the points in the test set. As you can see, for the easier set, most of the points, which cover the majority of the space, have the loss value near zero. And if we zoom in to this uncertain area, we can see the big difference between the accuracy of the neural network trained with uniform sampling and with BREED. BRID automatically discovers these hard areas and populates these regions with more points to expose the neural network to this uncertain area and therefore reducing the uncertainty. But now let's look at the actual dynamical system and actual surrogates. Physics-informed neural networks is one of the families of deep surrogates. The idea is to use the mathematical model of the system for training, since we do have it. Here we have an example, 1D Allen-Kahn equation. It's a reaction diffusion system which exhibits sharp gradients as the system progresses in time, which you can see on the image on the right top above. We want the neural network to approximate this unknown solution over the whole spatiotemporal domain, which you can see on the right below. And so to use the mathematical model for the training, we can impose the constraint on the neural network training to make it satisfy this differential equation across the domain. So we can differentiate our neural network according to the system and calculate if it satisfies this constraint or not. To do so, we will need to sample collocation points. Those are the points in the spatiotemporal domain at which we calculate this constraint. And then we calculate the residual loss by auto-differentiating the neural network at this point. As you can see, for this example, the placement of the collocation points is very important. It needs to be strategic. In this case, because of these sharp gradients, you need more points where the change is drastic so that you populate these areas with more points and the neural network is exposed to this area more. We benchmarked BRID for this case as well. On the left, you can see the test relative error progression over time of training. And we compare BRID to uniform baseline, where you just resample uniform with the collocation points, and to at the time state-of-the-art R3 method. In R3 method, in each round, the points which show above the average loss, they are retained for the next round. And every other point is just resampled uniformly. The difference with BRID is that BRID creates new points near the hard above average loss points, while in R3, they're just retained for the next operation. As well, the mixture between the uniform and non-uniform distribution is not controlled precisely with some hyperparameter as it's done in BRID. From the results, we can see that uniform made the pin converge only, as we repeat the experiment 5 times, with uniform pin converge only 1 out of 5 experiments, around 30,000 iterations. R3 did a bit better job with convergence 3 out of 5 experiments, a bit earlier, around 10 to 30,000 iterations. And finally, BRID made pin converge more reliably because it's 5 out of 5 times, and also faster at early iterations, around 5 to 8,000 iterations. Therefore, with BRID, pin converged better, was trained better, and at a lower cost. There is another family of deep surrogates, data-driven surrogates. The idea is that we want to use the simulation data. Compared to PIN, we didn't need it because we just used the model. Here we need to actually have the ground truth solutions from the solver. And as well, we can reuse the methodology from the computer vision and language processing because these are methodology which is established well for data-based or observation-based tasks. And here we will also have our data. Say we have a solver S for our system F with some parameters lambda, which control the behavior of the system. It can also control the initial state of the solution. The solver produces the solution for the system at some points discretized over the space. The resolution of the discretization is chosen by ourselves as well. Then the solver produces the trajectory of solution states by taking the preceding state and providing the next one, so iteratively. So our simulation data to train accurate surrogate, we need to sample a lot of these lambda parameters so that it represents well our training data for the surrogate. And then each of these samples for data are a large series of meshes. And as well, we need to wait for the solver to produce these samples, which takes large compute cost, as we already established in the start. So every data sample comes at a large cost. And active learning here can help a lot because it will reduce the number of data that is needed to achieve some quality of the training, same as it was with pins. But how to do active learning for data-driven surrogates? In the previous example, we were choosing the spatio-temporal points in continuous space, which is directly the data used for pins. In this case, we are not choosing the data directly, the solution states produced by the solver. Instead, we're choosing parameters which would create this data. So it's an additional layer of parameterization of choice, which is not so obvious. Which brings us to the next contribution of mine, online active learning. Sorry. So currently, the training workflow proceeds in rounds. We generate the data with solvers, provide it for the neural network to train on, and then we make decision about the next round of the data to generate with the solvers. But what if we could do everything simultaneously? Here we have the solvers running in parallel to the neural network training and to the active learning process to make the decisions. The solvers produce the data and send it directly to the neural network, so it's training with more data. And it sends the feedback about its states continuously to the active learning, so the decisions about the next solver can be done as soon as possible. With this continuous feedback loop, we would increase the impact of each solver run, as we can make decisions online. So how to achieve this system? Well, luckily, we have Melissa framework, which already solves just part of the system, specifically the online training of the surrogate itself. This framework is built as an architecture of clients and servers. So the clients, there are k concurrent solvers running in parallel and sending data directly to the neural network, which is on the server process. In this case, Melissa avoids storage. What it means is that the states from the solver are sent as soon as produced to the server, directly to the fixed capacity memory buffer. And then, as Melissa aims as a framework for high performance computing infrastructures applications, like on supercomputers, one of the main goals is to avoid any idle resources in the process. What this means is that the neural network is trained as long as there is some data in the buffer, and the solvers are running as long as there is some samples in the buffer which were already seen by the neural network, meaning that they can be removed and substituted with newly generated data. But Melissa doesn't have the active learning infrastructure. So how to implement one? I implemented the active learning infrastructure in Melissa with two goals in mind. First, as we don't want to have any idle time for the resources, we should not make the active learning process pause the training or the solver execution. Otherwise, it brings these idle delays. And then we will run the active learning process in parallel, concurrently, asynchronously to the solvers and training server. In this case, however, as the active learning process takes some time, During this time, the neural network is also trained and the data by the solvers is produced, meaning that there will be some delay between when the neural network gave the feedback about its state of uncertainty to the active learning process. Then it will take some time to communicate these new decisions about the next data to be generated to the solvers. And then finally, when the solver sent this actively chosen data to the training of the neural network, it's possible that this data is not as hard as it was before. Therefore, it decreases the effectiveness of the active learning decision. Therefore, we can do something like this. I implemented the active sampling mechanism in Melissa, which achieves both of these goals, communicating the new data directly to the solvers as soon as possible. For this setting, breed method also needs to be adapted. First of all, we don't have the set of all past samples on which we could make our decision. And also we are required not to pose the neural network, meaning that we can't score the loss additionally based on the up-to-date state of the neural network. So what we can do is to have a population of M most recently seen parameters, not the parameters themselves, but the data that is associated with these parameters and that was used during the training. And then, as we can score the loss additionally, we can just use already computed loss during the training. It will be historical, out-of-date loss, but still it is information which we can get for free. And then, as the loss progresses, we need to normalize it to have a better view on the value across the training. And as well, I additionally add a threshold on this loss to concentrate more on harder samples. And finally, the loss values now are produced for every state of the trajectory. And also, it can be that some state sample was seen by the neural network several times. So we have several loss values for one parameter lambda. So we just aggregate it by average. So we have one value for weighting our Gaussian mixture with centers at this lambda from the population Q. What we get is the proposal, which is based on the most up-to-date information about the neural network training. And the weights are proportional to the, on average, harder samples across the trajectory, which were exhibited during the training. We benchmarked this breed on one-dimensional PDs of different difficulty and dynamics. First is Korteweg-de Vries equation. It's a nonlinear equation which describes the system of wave propagation in time. And the second is Kuramoto-Sivashinsky, which is known for its chaotic behavior, meaning that from the initial state, it can change to very different outcomes. As an initial condition for the system, we can take a family of functions representing waves superposition. And then the task of the active learning is to curate this initial state, which is parameterized through the parameters lambda. In this case, these are the amplitudes of the waves and the phases. I show here some of the results. On the left, we can see test loss distribution over the amplitudes of the waves for the test set. As we can see from the picture below, the neural network which was trained with a uniform sampling, it shows elevated loss for samples where the amplitudes are high. When the initial state is created with a high amplitudes, it results in a very dynamic system, which changes relatively quickly. As you can see from the picture above, or neural network which was trained with breed, it again automatically discovers these regions even in the parameterized space. and lowers the loss values for the neural network, makes it less uncertain about it. On the right, we can see the test loss progression over training time. For this case, the experiments are repeated 9 times. Here we see the first column average loss over the test set, then the maximum error over the set, and the deviation over the set. So we look not only at the average performance, but also the tail distribution performance. Here we see that with breed, the neural network does converge on average for the average performance to a lower value, but not as big difference as we've seen in the previous benchmarks. However, still it does. But when we look at the tail performance, the difference is much more distinct. We can see that with uniform sampling, the neural network achieved the maximum error at the end of the training, the same that with breed, the neural network achieved at around 30% of the whole training time. What this means is that since we're working in online setting, every training iterations, we produce data. So 30% less training time equals 30% less data created. Therefore, with breed, we have a more reliable performance with fewer data, and so with lower cost. Main limitation of breed comes from how the proposal is built. It's a mixture of Gaussian kernels, meaning that the proposal is always anchored at these visited samples before. It doesn't have the global view of the space. Then we use the fixed isotropic Gaussian kernels, which can be blind to local geometry. We could use anisotropic kernels, but this would mean that we will need also to learn not only the centers of the Gaussian kernels, but also the covariance matrix. And in general, it would require more hyperparameters to tune. It will be just more complex. And then also Gaussian mixture performs poor in higher dimensions, as you would need more points to cover the space sufficiently. Again, the anisotropic kernels can help with that, but unfortunately, sampling from such distribution requires cubic time compared to linear for isotropic kernels, which were chosen for this reason as well. So the Gaussian mixture is just not scalable. Could we approximate this distribution better? Which brings us to the last contribution, UGA's method. So we can reformulate the query synthesis active learning problem differently. Say we define the epsilon, a variable which is proportional to expected error level. And then we can train a generative neural network, which would... Can someone please close the door? Thank you. So we can train a generative neural network, which would learn distribution of parameters given this expected error level. And then when we want to sample new parameters for creating our data, instead of being based on the previous one from the previous rounds, instead, we can sample desired error level from some prior distribution, then push it for the neural network, and it will provide us a distribution over the parameter space, which is relevant to this expected error level. We implemented UGA's method, online generative active sampling. Here, the generative neural network, is a fast conditional diffusion model. the epsilon we define as a standardized loss with moving statistics over training. And then now the OGAS lives in this parallel active learning process in Melissa. So the training data for this generator, the pairs lambda, the parameters, and epsilon computed error level are sent to some buffer on this process so that the neural network can continuously train from this most recent data. And since the diffusion model is fast in this context, it can train pretty fast and adapt to the neural network evolution, to the surrogate evolution also fast. To create the new parameters, we choose the prior over epsilon, epsilon, to be proportional to the epsilon value itself, meaning that higher error level, we will have more points associated with this error level. And then similar to the previous method breed, we mix it with the uniform distribution to ensure exploration. I also forgot to say the point about the corrected objective. I will just quickly come back to that. So the same mode collapse that we've seen to be tried to mitigate with the uniform mixing in breed, we can actually correct the objective of the neural network itself with importance weights. We evaluated this method on an extensive benchmark. There are 3 two-dimensional PDEs of higher resolution, and there are 3 different surrogate architectures, which are having different backbone and different size of it also. In this evaluation, the task of the active learning to curate not only the initial condition parameters like it was before, but also the parameters of the PDEs themselves. In total, the dimensionality of this parametric space is much higher than it was before. It's up to almost 300 parameters compared to 4 in the benchmark for Koromoto-Sivashinsky and KTV, or even 2 for pins. So how did it show itself? So here I show some of the results of the experiments. First, you can see the table with neural network performance at the end of the training, the average loss, the deviation, and maximum. So again, we look at the tail performance. First, it's for Kuramoto-Sivashinsky PDE, the same we've seen before, the chaotic one. And the surrogate architecture is a Fourier neural operator with 28 million parameters. As you can see, OGAS and other active learning methods decreased the average performance of the surrogate. As you can see, uniform has the best one because it's lower. Lower is better. Forgot to add it. But then when we look at the tail performance, every active learning method improves the tail performance, and OGAS is actually the best. And then for another PDE, Navier-Stokes PDE, it's a PDE which is used in computational fluid dynamics. And the surrogate architecture is an operator transformer, Scott, with 180 million parameters. For this case, OGAS improved all 3 metrics, the average, the deviation, and the maximum. So what we can see from this result is that for a relatively harder task with a small model, the improvement in the tail performance comes at the cost of average performance. And for a bigger model on a relatively simpler PD, the model is capable to learn both the hard data and overall not lose information about everything else in the system. On the right, you can see visually what is the effect of the active learning, in this case OGAS, on the surrogate predictions. You can see in the first row the ground truth states from the solver. In the middle row is OGAS, and the bottom is the uniform. In the first column, there are the results for Navier-Stokes. It's one trajectory state. So we can see in this area, which I highlighted by the green square, the model trained with OGAS managed to capture, not exactly, but managed to capture these two vortexes there. And then the uniform, the surrogate just lost this information for this state. Similar effect we can see for the other PDs that were studied in this experiment. To conclude, I will first drink water. We started with a research question, how to improve the training of the deep learning surrogates, in this case with query synthesis active learning. First, implemented BRID, a simpler distribution approximation method driven by laws. Then we added the online active learning with the active sampling mechanism in Melissa to maintain this continuous feedback loop with a low latency. And adjusted and adapted and improved the sampling mechanism itself with a more sophisticated generative neural network sampling, which allows us to scale to higher parameter spaces. What are the key insights from these results overall? We never tried to change the architecture of the surrogate itself. All the improvements in the performance came just from choosing the data more strategically. By choosing this data strategically, when we're able to navigate this complex high-dimensional parameter space, for data-driven surrogates, we reduce the number of data needed for training these surrogates better. We also see that the benefits that come from the active learning are dependent on the model capacity, as we've seen from the results on the previous slide. The better the model, the more active learning can help it. Since the model with bigger capacity or sufficient capacity for the given task can better learn the uncertainty in the data. So there is a trade-off between this mean performance and tail performance, which can be a different goal in different applications, and also highlights that we need to choose the surrogate model appropriate for the task. And then with this online feedback, we're making every solver call exploited to the maximum, because with the continuous feedback, we make decisions about the data as soon as possible and expose to the neural network this needed for the training data as soon as we can. And so what is next? There are some short-term ideas for online query synthesis active learning. First, gain popularity foundational models in AI for scientific computing. Those are models that are pre-trained on different types of PDs and then can be used for some downstream tasks. In this case, this pre-training data that needs to be created has to sufficiently represent different systems, and it requires just a lot of data. Active learning can help in that by choosing the PD types. Some PDs can be harder, some PDs can be easier. As well, choosing the type of the initial condition, for example, not only the wave superposition, but other types that can be more suitable for different PD types. And as well, it needs to handle heterogeneity in the parameters, which can be different for different PD types. Next, over the course of this thesis, and in general in the field, the main focus take the regular grids. So when we have the discretization of the solution over uniform regular mesh. However, for more large scale, industrial scale, and also science relevant applications and systems, they often use more complex geometries and structured meshes. And so the active learning can help to choose the types of geometries or specific configurations of the geometries with some parameters, or even the points in the geometry space. As well, some ideas of the query synthesis active learning and challenges do intersect with other well-established fields, like simulation-based inference. This is the task where you need to perform the inverse task instead of the forward. So instead of predicting, for example, from the parameters the solution state, you want from the state of the system, from observation, find what were the parameters that created this system. In this case, this task is solved by using the solver's simulation data. So very similar context. As well, reinforcement learning shares some ideas, for example, the exploration-exploitation dilemma, also the online system often performed the training of the agent in reinforcement learning together. And as well, active learning can potentially be formulated as a reinforcement learning task. More open question. At what point does learning how to learn better is actually harder than just to learn on whatever data you have? Because maybe choosing geometries and points will be just too hard, or trying to generate directly the states in the solution as the active learning is choosing not the parameters, but the states themselves. Maybe it's better for some tasks, or in some cases, to just stay with the uniform sampling. And I would like to end with a more of a social society, a relevant note. So this thesis was trying to reduce the cost of training the deep surrogates, which are trying to reduce the cost of obtaining the simulation data. All of this computational cost always comes with some carbon footprint because we're running computers all the time with big data centers, etc. And so while I was trying to solve this problem, actually, I also emitted quite a lot of cost, which I want to make everyone mindful about this effect, that every efficient path comes with some cost. And during the thesis, my experiments emitted about 4 tons of CO2, which is twice the goal of a better planet, which is supposed to be 2 tons per person. And this is just experiments. So thank you. I'm sorry, though, but thank you.
Perhaps you can take a 2 or 3 minutes break if some people in the room do not want to attend the room during the questions. And just to let Sofya have the time to drink.
To breathe.
To breathe and to eat, yeah.
Thank you.
You're ready to start questions? To stay with you? Yes. Okay.
How should I stay the same way?
You stay here. Yeah.
Okay.
Try to put all these ones.
Yes, yes. I could put the Zoom videos maybe there. That's what you meant? Like so that we can see
Yes,
we can see the other
the jury, the
Yeah.
people asking questions.
otherwise it's a bit weird to just talk to the computer. So.
Yeah.
Or maybe it's okay.
Yeah,
I don't know if Ronan is possible.
But maybe when he will start speaking, he will go.
Maybe, yeah. Or maybe if I click this. I don't know. How is better?
Smaller, probably.
Smaller, yes. How do I do this? Oh my God, I'm sorry.
No, you were good.
Okay, I'm sorry. Please show me the I'm sorry.
This one here. Yeah, it's perfect like this.
Why can't I come?
Leave it like this, I think.
What? Okay.
Yeah. Okay. So we can start with the question session.
The most interesting.
So we'll start with two referees. So first, Ronan in Brest.
Yes. Can you hear me?
Yes. Great.
Thanks, Eric, for the introduction. Congratulations, Sofya. I really enjoyed your presentation. And as you raised it during the introduction and conclusion, you addressed very timely scientific topics regarding the training of neural emulators in different fields. So you probably know I'm more interested in application to ocean regarding AI. And we've been discussing this quite a lot with Julien this summer in Grenoble, this active learning. And we never been really into investigating this. So it was really an opportunity for me through your manuscript and your presentation to dig in the literature and understand more what's the state of the art. So at the end of my question station, I have this question regarding whether we could apply this to ocean modeling and ocean cases, but that would be the last one probably. But really, yeah. And I was really impressed by the fact that you covered both like more theoretical aspects regarding the probabilistic modeling, the way to apply or use established setting like diffusion models, units, or importance sampling, and the way you can bring this to up to at-scale demonstration. And I was also really impressed by the experimental setting and the comprehensive analysis you're doing your work. So yeah, and I mentioned this during my report that I think it's the same with the presentation. Your material are really clear, well illustrated, and so you conveyed very nice way all the contribution you brought through your work. So now I move to the obviously, but congratulations for it. So now I move to questions. Probably my first question is I was wondering whether we know what's the optimal sampling prior in some sense, so that we get the best training of a neural network. So maybe if we focus on the emulator, like more the second part, and I don't know whether you have some you can discuss a bit whether we have like theoretical guarantees regarding some what could be the optimal sampling prior, whether it could exist or not. And my related question is whether I think it makes perfectly sense to sample some specific data where you have large errors. But my question there is whether that could also lead to some bias in the estimate of the neural emulator. So yeah, maybe if you could first start, and maybe I could explain why I think I don't know, but I think that maybe there could be some kind of biases. So whether you could first discuss whether you could provide like some kind of theoretical analysis or guarantees regarding the optimality of this sampling of the data.
Okay, thank you for questions. So the first one about the theoretical guarantees and optimality. So there are some theoretical guarantees for active learning in very simpler tasks. And for example, there is a recent work about how active sampling is more optimal for neural operators for linear systems. And it was most important is that, okay, exactly connected to this work, at least, we operate also in online. So this kind of adds all kind of difficulties in making theoretical guarantees to not be too complex, because usually you would try to do theoretical guarantees for, oh, let's try to simplify this and that, and then you can try to find some actual convergency levels, I forgot, rates or convergence rates. And so again, there is these theoretical guarantees which are coming from active learning. They're mostly for the pool-based methods. Usually they are connected with the uncertainty estimations more than to the loss. There are some works that connect that the loss is representative of the uncertainty, but again, it's like, okay, let's try to simplify, then the loss will work. And so during my work, while I did attempt to try to find some theoretical grounds to make it more supported by the math and not just experiments, I did not manage to do so. I was more focused on establishing the empirical results, so trying to provide the results which are experimented with different models for different tasks, just a lot of seeds, just to at least try to give the idea what is possible before the theoretical guarantees can come after. And so, let's say, within this work, there are no theoretical guarantees established during the work, but I think it is. So I forgot how exactly was the question posed, like, is it if it is possible or if there are some, like.
There are some.
If there are some, okay.
Okay.
Or this specific case with the surrogates and active learning, exactly query synthesis one, there are no, and not produced during the thesis. No.
Okay, I understand this, but it was just, because you showed that, and that was nice that you get a better behavior for the tail of the distribution. So you have like tail-related metrics where you show larger improvements. So I was wondering whether that was somehow through the active learning a way to bias a bit, or to better account for the tail, maybe to bias the model towards the tails. And the reason for this. The reason for which I was questioning this is that regarding the emulator, I guess that what we try, the learning is based on usually on some kind of MSE. So you try to probably get some kind of estimation of the expectation, of a conditional expectation. And there usually the conditional expectation is, it relates to minimizing some MSE with respect to the prior distribution of the data. So. And here you try not to sample the prior, but to try to sample another distribution where you provide more weight to some specific data. So in that sense, I was thinking that maybe you do not get an approximation of the mean square error and then conditional expectation, but maybe something else. But it's just.
I think I understood what you mean. So trying to use the different information for the sampling. So there is like, if I understood again the question, so if there are other sources that can be more biased to different specific goals, as a what to bias onto, so like conditional to this area. So for example, in pins, there are some works which are not using the loss itself, but some different information. For example, the NTK, the neural tangent kernel. So it's more about the gradient information, more about the, let's say, direction of the model, the optimal direction of the weights to go depending on which data is given. But however, while this, also this actually information can be even more or less stationary to the neural network evolving, because, well, you're kind of fixing the task itself, and then if you fix the model itself. But computing the NTK is super expensive because it needs the gradients, and in pins it's a bit simpler because, well, at least you don't need to create all the data, you can just evaluate the points. And so then there is also another thing. So, for example, this NTK, I don't think it's very scalable to data-driven surrogates, but there are other active learning criteria for the information. So not only the uncertainty, but the information gain. So expected improvement of the model, expected change of the model, which probably could also be used. But again, if we're scaling to huge data-driven surrogates, I think that's just going to be getting more expensive, because usually you want to evaluate some points for this information criteria, and then these points you usually, if you want some new points which were not in the training data but additional ones, then you need to create the data, and maybe it was not necessary for the training but just to compute the information criteria, so it can be very complex. And then also, for example, here we were using the squared loss with breed mostly, but then for OGAS it was the standardized and also normalized, actually the scaled. I just put details a bit away from the main ideas. So there, for example, you could use the loss value itself, or you could also scale it to the norm of the sample itself. So it will be kind of more relative, for example, to the amplitude of the values. And this can work better. And also, for example, again, we could try to impose somehow the maximum, the worst error, or even distribution of the errors across the state space. Maybe these are some other interesting ideas in this case. And also, you mentioned something about, let's say, saying that, on mean performance, it's not as a big change as for the tail performance, and we see the big change for the tail performance. This actually also can be, it can be controlled, for example, with this mixture of uniform. So you could have more uniform samples and then, or like less uniform samples, and then you want to even more improve the tail performance. So there is also this way of trying to adapt the prior for specific task. For example, when you're really, you don't, let's say it's not like you don't care, but the tail performance is much more important than the average. For example, you're okay if the average will degrade by a few percent, but if you manage to improve the tail performance by 100%, I don't know, like by big changes for some, indeed, applications like where it's like sensitive applications, like when it's very important to the reliability of the model rather than just average performance. It's also possible to control through this. I hope I answered some of your questions.
It's fine.
It's a little bit hard for the Zoom to fully understand the questions.
No, but this was a really open question. So
yeah,
sure. So it allows me then to jump to the part where you the active learning and Melissa and the way you parameterize the your sampling. So if I correctly understand, both in the Gaussian case and with a diffusion model, you have some kind of conditional sampling. But I understand that the conditioning is not the same. If in the Gaussian case, you could probably, I assume we can interpret your model as a conditional sampling where the conditions are provided by the current members in your current data set. And I understand that with the diffusion models, the conditioning is, and that was the epsilon. So in your slides, if I'm not mistaken, and it's the error, so of the loss. So my question here is why I wasn't sure to understand why in the diffusion when considering the diffusion model, you considered this conditional parameterization with respect to the loss and not something similar in some sense to what you've done with the Gaussian case, where you have this conditional parameterization with respect to the members or the different samples in your data set. So could you maybe explain me a bit what you expect from this parameterization here and what's the reasons for this choice here and the difference with what you did with the Gaussian case?
So let's say, first of all, the Gaussian mixture is also in a way conditioned to the loss, just not explicitly, because you're having the, you do evaluate basically the loss distribution for these specific points in the training set. And then you're trying to, with this Gaussian mixture, to approximate basically this, let's say, it's not that it's not the same. Wait, let me just think for a moment.
It would be perfectly fine if there is no specific reason and just let's say that the prediction model was one choice and the diffusion model is another one.
The easy, let's say, answer to the part why the generative network is conditioned specifically like this, because it's much nicer to be able just to choose, oh, I want hard sample, so error level 1. I want average hardness sample level 0. And no, I mean, if it depends on the prior you're putting how the distribution of the epsilon is, but in our case, since they're standardized, 0 means the average error level, and positive values are harder samples. And so in this case, you can just choose these global conditional, like I want to have that many hard samples, that many simple ones, and maybe you want even to try to sample ones which are with negative values. So those are which are easy, and then maybe in this case you could even remove the mixture with a uniform and try to do it fully through this epsilon value, and then using just this kind of indicator, the signal of the hardness, you acquire this distribution over which lambda do correspond to them. And also you're getting the distribution, which is already nice. You don't have like point to point, you can have point and many points over the same value. And while in the breed with the Gaussian mixture, you just have to always have this which values were seen of the lambda, and then you re-score what was the progress of the neural network on these values. And then depending on them, you put your kernel. It can be not only Gaussian, it can be anything else, I guess, but it means that you are always, let's say, you have to be based on already created training data, on already chosen from the previous round's data to evaluate the neural network loss I forgot the word, or to keep track of how it changes.
But just to maybe just to be to better understand the epsilon here at one iteration of your algorithm. the epsilon here is the same for all the new samples you will generate, or you use a different epsilon value for each data you're gonna sample?
Yeah, I think this it's on the next slide, but anyway, it doesn't matter. I don't need the slide for this. So the epsilon is computed also according to the loss. So when there is a training iteration of the surrogate, you have the loss per sample of the surrogate in this batch. Then you normalize this loss according to how the loss changes, because you keep the running values of the average and variance so that you can standardize it after. And so basically epsilon here is just a rescaled, renormalized loss. So
but it's the average if that's the average over all the samples at a given iterations that you consider, or it's
it's per sample. So if you have trajectory. So it depends again on the model training. So in these experiments, it was model autoregressive. So you have the precedent state of the simulation and the next one, and then you compare with the ground truth, and then you obtain this one loss value for this pair of states, and then you have loss value for the data which was in the batch. But then let's say this is actually probably an interesting question, because in a way, since you have the data appearing in the Melissa buffer uniformly in terms of the training, this trajectory step t, in the end, this value is kind of an average over the trajectory in a way, because you're getting, let's say, instead of getting the loss per sample, you want to have this loss for these parameters over the trajectory. And so the model just learns to have produce the parameter lambda such that over the trajectory, all samples have at least expected this error level. Does this answer what you meant by the different states samples?
Yes. So somehow here you can consider this epsilon provides you some kind of non-local neighborhood if I try to understand connect to the Gaussian distribution, in the sense that you try to resample new data with the same level of errors, which rather than in a neighborhood of the state, but because the epsilon is specific to one sample, it's still conditioned by a given member in your data set. But then, do you think maybe here, have you explored also parameterization of this model? Typically, you could also have considered a conditioning by the state, by one member, one sample directly.
I didn't catch.
Here, have you explored my question here? Because it's so easy in neural network to change the inputs. So the inputs to your diffusion models could be epsilon and the simulated state, for example. So
training not on the pairs parameter and error level, but the actual state and error level. So I think this is possible in a way. I mean, no one says no. I mean, you can try to do that as well.
Yeah.
And I think this is one of the interesting also next steps. But I think the problem is that first of all, you make the neural network, this generator network, be dependable on the resolution. So if you have a large resolution, so discretization of the state, you would have to scale not only like the surrogate, but also the generative network is going to be dependent. So its size and how fast it trains going to be dependent on the discretization. And so in this case, for example, you have just the parameter lambda, which doesn't depend on the discretization resolution. So if I want to train the surrogate for 256, and then I go to 1000 by 1000, the neural network size will stay the same, which makes it scalable. And let's say the parameter space is also, well, at least if we're not talking about the geometry, but if we're talking just about all parameters of the initial condition function, parameters as a coefficient of the PD, etc., like these ones we already discussed, or others, like they're going to be smaller than the discretization resolution, at least in this case, but I don't know at which point it's going to be a lot of parameters as much as there is the resolution. So again, it's like the same with open question, at what point it's too hard to learn how to learn instead of actually learning. So I think it's kind of in this direction that, yes, you could definitely just make the conditioning, so trying to learn the distribution of lambda over epsilon. But then there is also another question, which actually what happens in the active learning for observation-based tasks is that maybe what the neural network will create, synthesize as the expected for this error level relevant data, it might be something that physically makes not much sense, and the solver will just not be able either to solve it, or it will, I mean, also like, what if the generator is not trained enough yet, and it will start to give this kind of incorrect, physically impossible, I don't know, data to the solver, and it will impact the training of the neural network, and it just, so working through parameters is easier for sure. I think that's the main reason to do through parameters like this.
Okay.
That's
Okay, thank you, Sofya. Do you have time for one last question, Eric?
Sure.
Okay. Maybe then I have a last question regarding the possible application of the same approach for, let's say, ocean modeling or climate modeling, so Earth system models, and possibly whether, I mean, I mean, do you just consider your approach off the shelf and we can directly apply it, or whether there are a number of challenges that needs to be addressed before being able to apply similar approaches?
Good, definitely good question. Let's say this is something that I was lacking during the thesis, to have some actual more closer to real life applications, because so far it was just like, oh, let's try to take this PDE. It doesn't really matter where it's applied exactly this, at least configuration. Let's say we're working in academic toy experiments still, and this is a very important question of the gap between these academic toy experiments and actual applications. And this is something that I would have loved to pursue during my thesis, and that's something that I would have changed probably about my PhD, is try to find someone to get this more closer to real world application. Maybe we should have talked about it earlier, right? But so I'm not super familiar with ocean Earth systems in general. What I understand is that what you could change is the like initial condition, and you have fixed geometry, and then maybe you have multi-resolution, or multi-physics, and you have maybe several layers. I mean, it depends, I guess. But I think
maybe here I understand that, yeah, if you can just maybe raise something more specific, I understand that typically the dimension entity of the initial condition and the number of parameters and the computational complexity of a code is larger. Let's say that the initial state would be like the same dimension as the ocean state, so it could be very, very large. Yeah. So maybe there might be a question regarding whether your approach can directly scale to an initial state, the lambda operator being like, I don't know, 10 power 5, 6 or more dimensional, or what you need to change.
You said 10 to 4 or
10, 6, I don't know, above 5, 6, something. And 6 would be very small, okay? But let's
10 to the 6.
Even 8 or 9.
Okay, yeah. Okay, I understood. But in this case, the initial state is the solution, the system state at the 0 state. So since I'm not familiar again, how do this initial condition are usually created? Like, is there already some initial condition, like something like, one from the past? Or is it something that you have a function to parameterize, like the same as with initial condition for the wave superposition or something like this?
No, I don't. Eric might know more here, but I don't think so. It's by itself a topic of interest to know how to sample good initial conditions. But I mean, we know that there are example diffusion models applied for the same level of complexity. I mean, diffusion models are applied for weather forecasting, which is the
I
same
mean, in
kind
this
of
case, maybe, I'm sorry, I think maybe in this case, because you don't know how to sample initial conditions, maybe it's possible to, indeed, with the diffusion, try to learn what initial conditions are possible, because in the end, I mean, as your trajectory progresses, any of them can be initial conditions, because it's, well, the same system, so maybe it can learn to generate those initial conditions, I guess. I mean, so 10 to the 569, I guess. For me, question would be how the deep surrogates even do they manage to work with this complexity? If yes, then probably the diffusion model can too. But then it means that you have additional model working on the same data, and then on the other hand, you could also try to apply some methods where you, for example, to estimate the uncertainty, you could try to have the model which already tries to give you the uncertainty estimates, like with the dropout, MC dropout, or to give directly the estimates. But it's not even the same. But maybe it could give like per point in the initial state, or honestly, I mean, potentially it can scale, but I think it will give this burden of having another model, which then maybe will not be able to learn as fast. But it can be interesting to try. But to be honest, I don't know. I mean, I can say, yeah, of course, let's try. But like, and then it's just a matter of actually trying. I think it's worth trying, I guess, but maybe not directly with such big size, maybe slightly less one, to see how much it can actually scale. And if it can work with this directly generating initial conditions, then if it will work, then why not?
Okay, thanks a lot for your responses. And again, congratulations for your work in representation today.
Thank you.
That's it for me.
Ronan. Okay, so the second jury was Mathias.
Okay, yeah, can you hear me well?
Very well.
Very well, yes.
Okay, great. Yeah, so I want to second what Ronan said. Great presentation and a very timely topic. I also like it because we are also working on a similar.
That's why you're here.
Yeah, exactly.
In a way.
That's why I'm here. Yeah, let me start off with a question about generally kind of active learning. So you started your presentation and also your thesis by showing that active learning oftentimes leverages uncertainty, right? So you have oftentimes acquisition functions based on uncertainty, or also typically distances between data points.
Yeah, the diversity, distance.
And then you also had in your toy example, right, this example that there is a region in your kind of input space where you have more uncertainty. But typically, right, what you do is you actually want to capture model uncertainty, right? So typically these methods look at epistemic uncertainty and try to figure out like where is the machine learning model uncertain. Yep. And an advantage of this is that you actually do not have to have access to the loss function, right? You don't have to be able to evaluate the loss function at the points where you want to measure uncertainty.
Yep. That's why we try to use loss in a way.
Yeah, but this is kind of bringing me then to the question, right? So you started off this way, but as far as I understand, most of your methods are actually based on the loss functions, right? So the residuals in the case of pins.
Most of them, at least.
Right. And so my question is here, like, in what sense is this limiting or maybe a problem? Because I assume that, when you start off with the initial sample, it's very much dependent on where you actually collect these loss points, right? If you are initially starting off in a region or in a bad area of your space, it's much more difficult actually to explore other parts of the space if you're just relying essentially on the points where you have the loss function at your disposal. So I was kind of wondering, how sensitive is your method generally to this initial, points that you're sampling and for which you then have the loss and for where you then start actually your exploration from, right? Because you don't have access to other points.
Yes, so there are maybe two questions within this question. So first, so I do know that loss is let's say it's a noisy proxy to the uncertainty. It's not going to be always exactly it can be representing well the uncertainty model at some point, or it can be very also sensitive to the model updates, etc. But still, what is very good about loss is that you're getting it for free just during the training. So I think compared to uncertainty, so for example, for pool-based methods, you can have all of these initial sampling points, and then you would need to calculate the uncertainty for all of them and then select the best one. Or for example, in the methods for OGAS experiments, there was not only OGAS, which is based on the loss, but let's say I represented it more about the loss because breed was also loss driven. So it's more about comparing breed versus OGAS. It was also trying to use the uncertainty estimates as well. So what it would be doing is that you would have so in the experiments there, it was the ensemble of two surrogates directly. So you would need to get the uncertainty by doing this forward pass and computing the discrepancy between the outputs of the ensemble. And let's say in this case, it's even also some kind of not a good maybe estimate of the uncertainty because maybe you would want to have more members in the ensemble, or maybe you would want to have the model which already have this either MC dropout or something that predicts not only the state but the uncertainty. But then you're kind of in order to do the active learning, you're trying to make some changes to this surrogate model itself because maybe you want just to have a surrogate without any changes. Like you don't want to have the MC dropout and you don't want to train two ensembles. But in case with the loss, you can work with one model, no changes needed. But then indeed, as you say, so the second kind of part about the basically under exploration and mode collapse, etc. That's why probably for breed, it was so important to have this uniform mixture. So within the thesis, well, it was not published, but I was trying to have different strategies for how to mix with the uniform. And you could see that it can, let's say, so I think that's why breed, for example, was showing worse results than OGAS in the experiments because it was exactly doing what you're saying. It was really concentrating on the hardest points and not really exploring others because just the uniform mixing was not enough, while OGAS was able to have more of a global view on the space. So it was able to explore other new points, completely new points, because they're not based on like this progression of the things. Yes, did I partially answer, or maybe you could repeat what is left?
Yes. So I guess I took that the answer is yes, it can be limiting, right? Because you kind of you assume that you have access to the loss, so you can only look at the points that you currently have and then start your exploration from there.
Yeah.
And so it might be more difficult to kind of get out of, let's say, local of local regions that you haven't covered with the initial
this I forgot to
samples that you got. And so then adding random samples makes, of course, a lot of sense, right? Because then you kind of automatically cover globally the input space. Have you kind of, because you mentioned, right, that this is really helpful to combine like, uniform sampling, so some form of uniform sampling and the loss-based sampling that you designed. Have you analyzed this in a bit more detail? Like, so how much, what fraction of, let's say, uniform sampling is more helpful? Have you kind of experimented with that a little bit, or?
Yes, I did. Actually, so for example, on the slide, I could open, but it's like this alpha value, which is the mixture between the uniform and the Gaussian mixture. It's not fixed during the training, and well, it's first linearly grows, and then it is fixed to some constant. So it's kind of a following this curriculum learning. Like you have first more exploration, then you start to exploit more. So you first have like more of a simpler samples and you have harder samples. And so I was like in my first year, I think, when I was doing this mixture, I was trying to do like, oh, what if it's just constant? What if it's just linear? Like linear, like to some point, I mean, longer point, or like if it would be some step function, if it would be some polynomial, like there are a lot of different ways, but in the end, exactly this schedule of first linear from some starting point, usually non-zero, but it again depends very much on the task. But for simpler tasks, it can start quite high, this alpha ratio, so you can start directly with the harder points, but it's always bad to have the alpha near 1 in the end, exactly for this point of you're losing this exploration part. And that's why it's good with the OGAS, you can actually not have these mix with the uniform. Maybe you can try to control through the epsilon itself. Maybe you can actually even try to see like, you could do some kind of which samples are like you can do something like which samples were not seen, for example. Like if you put I don't know, like you can have more control for this epsilon because of this more global view on the space, etc. And so, for example, in most of my experiments, I think I was using something like something starts with 30% of concentrated, then it grows linearly for quite short amount of time. Like it's not like a half of the training time. It's more like maybe 15%, then depends. And then it grows up to like 75%, for example. Or sometimes it was from 70 to 90, and then but it depends on the task. But it was some kind of, but again, this why it was also like, it was very sensitive to this alpha debris because it doesn't have its own exploration part as OGAS does. And so it would be very sensitive, but you have this at least 3 parameters. So what's the starting, what's the ending of the linears, and how long it's growing linearly. So you have at least 3 parameters just to control the uniform. In case of OGAS, it's not growing linearly, I think. I think it's just constant to some value. It's more of exactly this trade-off on the performance versus average. Because,
Okay, yeah, thanks. Let me then in this area ask one more question. So have you because right, so you started with this kind of uncertainty, the description of active learning oftentimes using uncertainty. Have you actually analyzed also by chance, just out of curiosity, how well your method of proposing new input parameters in the active learning loop with uncertainty of the model? So is the epistemic uncertainty kind of highly correlated with the proposals that your model actually makes?
No.
Okay.
I haven't tried. I think it's actually interesting thing to do as a like of a checking that the method actually does what you want to do. But let's say there is one thing which is maybe in a way is interesting. Let's say, so it's not connected directly to actually calculating uncertainty values and try to make the correlation. But let's say with these examples where let's say you kind of have this understanding where it will be uncertain, like high-loss area, like high amplitude states, or one of the experiments, there is this heat PD where you choose the temperature on the box outer edges and inside. It could also be like, what's the difference between all of these temperatures? And if you have high difference, then it's harder dynamic. And so you will see that BRID does find this area itself, but of course it's not the uncertainty estimates the SMs, but it's like more of I think it does what I kind of expected by its own. We're just using the loss. Mm-hmm. So okay. But it's never tried to actually do this kind of analysis post-hoc.
Okay, yeah, thanks. That was just out of curiosity, not that I think that you should have.
I will just add one comment because you said about the uncertainty, epistemic uncertainty and all. So I think what is also very interesting in this case for surrogates and for synthetic data is that in a way we don't have the aleatoric one because, well, we don't have observations, which can have this noise in the data. I think that's also why maybe the uncertainty estimates can be very interesting in this case for synthetic data, because you have, let's say, I can't say there is no aleatoric. I mean, I don't know for sure, but I think there is most of the uncertainty comes exactly from the model itself. And so then there is some also understanding that the epistemic is uncertainty from the model, so from her capability to catch the model, so like the uncertainty. And then there is the uncertainty which comes from I didn't see enough data. And so basically active learning, and why we want to have these uncertainty estimates and then the loss is because we're trying to decrease the uncertainty which comes from the knowledge about the data. And that's why we also see, I think, this effect of model not capable, because you're not being able to decrease uncertainty which comes from the model itself. Like you can decrease only what data you can give to the model. So the uncertainty about the how much you gave, because potentially we can give as much data as we want also. But yeah, just also I think why it's important to look at the uncertainty, not just the loss. But I think the loss was just the choice because you have it for free during the training. And it's a nice way to reduce already big costs, etc.
Okay, so let me move on to the kind of the second, what you called your second contribution, which is this kind of online training. So here I was kind of wondering, right? So here you're arguing instead of kind of collecting data points iteratively, adding them to like a database of data points and then retrain the model over and over. You kind of do everything at the same time, kind of, right?
Yeah, you don't. So yeah, so, I'm sorry. I let you finish. I didn't. I thought it was.
Yeah, and so just to repeat and to make sure that I understand correctly, and so I was wondering, how challenging is this, right? Because and also, did you compare this to actually doing where you collect all the data over time, yeah, when using your approach, and then to retrain the model on all of the data from scratch, right? Because in our experience, for instance, I think you mentioned also catastrophic forgetting, right? If you kind of just iteratively update the model with the incoming new data points that you have, you might get some really bad kind of like drifting behavior of the model, right? And so it kind of then forgets about previous samples. So I was wondering, how complicated was it to find the right balance here between, using these buffers and throwing away older, data points and keeping the newer ones? And so what was your experience there?
Interesting question posed as what your experience, not actual. What's the answer? So one thing, so no, we did not try to retrain the model on actively collected data, which is supposed to be better data set for training. Because let's say it would be interesting to see for the research question of does it make it actually better if we do it like this? But then it's kind of it can give us some insights, but I think in the end it's not the task we're putting ourselves to do with, like, we're trying to put ourselves in like actual task, like, oh, we have the model to train continuously on the data. So in this online context, or even not online, let's say you have data, but let's say I would like to do, for example, something like, rather maybe not this, but so one of the interesting directions is like, okay, you train some model with this active training, and then you know which data can be useful for training of this model, but maybe it can be also transferred as a data set then for training. And so like, instead of creating the training data sets, like, I don't know, CIFAR, etc., like this kind of benchmark data sets for training, maybe it's possible to apply active learning for this. And then maybe it would make sense to do this, like trying to see if with this collected data set it will work. It just didn't have time to try to do this, but I think this can be interesting because also I'm curious if it would be like, let's not try to train even like actual surrogate, but like some smaller model, which would be just something that gives you the idea what any model could give as a hard samples, etc. Like some kind of a initial, at least instead of a uniform, you would have something else. So there is this, and then the experience with the buffers, etc. So I think.
So did you use always batch size 1? Did you, right? So because you get incoming new data points from your numerical solvers, right? So
Yeah,
did you just use like batch size 1 every time a new data point comes in? You just train the model on that and from like warm started or?
No, so in the online setting, let's say the training of the surrogate, or at least the process is not dependent on the receiving side. It just has this whatever there is in the buffer, and it samples the batch of whatever size we choose from what we have in the buffer. So if you have the buffer size, I don't know, 500, and you have the batch size 10, it will select 10 points from there. And it's just actively changing buffer. And so when the data is received, it just does some updates, like it's looking that there is some samples that were seen, so we remove them, put new one that's unseen. And it's they're asynchronous in terms of like the training is just, I have the buffer, I train on it. It's the same as it would be some storage data set. It's disconnected, it's not dependent on the receiving side. It's two different processes. And then the receiving, it just trains as much, but so potentially the surrogate is, the GPU is always running, it's always training. And then there is, of course, the problem that if the solvers provide the data for too long, it can incur this kind of, I overtrained on this buffer, but this is the problem. I don't know how to solve, let's say. I think it just at some point, maybe this online setting doesn't work for this specific case, or maybe it should be somehow adapted to do something about it, let's say. And then also the buffer itself, for example, it's not, the eviction of the sample which was seen is done just if seen, remove, if not seen, don't remove. So for example, there it could also be the active sampling, let's say, or active learning inside there. So don't delete it if it was seen recently, or delete it if it was old and seen, or maybe you can even recalculate the probability of deletion based on the model and something like this. And then the buffer size also does affect the active learning and the model training in general, but also the active learning, because if you have the buffer size too big, let's say you have 500, and you receive one by one this newly actively selected data, it takes only 1 out of 500 as actively selected. But then if you have and so the probability to get this actively selected sample is lower. And then actually the buffers of smaller size work better because you have higher portion of this actively selected recently data. It's the update of the buffer. It's faster. So it's kind of interesting that it's in a way contradicts to like, we are imposing more updates to the data and it's actually working better. But I think it's just maybe the effect of specific tasks, specific model is different. And in the end, we do still mix it with the uniform. So I guess it just, the mixing with the uniform just helps with the catastrophic forgetting as well. But I think this is also like why I really like this online setting is that you don't need to retrain the model from the start, because if you have the foundation model again, you usually don't do that. I mean, you're pre-training it for weeks, you will not do this, you will not retrain it every time new data comes. I mean, when you do this decision about run base, so exactly for the reasons of, or you have a solver which runs not for 1 second, but for like, 10 minutes or something. And then you have foundation model, which is just running for a long time. So let's say, I think let's say for the experimental, for academic experiments, it's or for testing and developing the better surrogate, etc. Online maybe doesn't work necessarily. I mean, you have to restart the experiment. But then for this kind of deploying, like, okay, we now run for 2-3 weeks. I think that for this it works. I think this suits very well. In
Okay.
this case.
Great, thanks. One last quick question about you mentioned in the future work section of your talk, you mentioned foundation models. Can you say a few more words on how you imagine active learning to play a role there? Are you imagining it to figure out what data to generate for pre-training a foundation model or for fine-tuning it, or what are your thoughts there?
So I think it can work for both parts. I mean, but I think it's even more important for the pre-training, because usually for pre-training you need like really a lot of data of different. Let's say if you want to train a model which is pre-trained on diffusion and I don't know Kuramoto-Siwashinsky, like both of them. I mean, probably not necessarily the case, but let's say you don't want to have 100 samples of diffusion and 100 samples of Kuramoto-Siwashinsky. You probably want different distribution, and let's say you can, of course, yourself heuristically find what should be the proportion in the data set for pre-training of one or another type of PD, but maybe it's not always obvious, and especially if we then talk not only about the just type of PD, but then also type of initial condition. So like really choosing the distribution of like this choice, like discrete choice, but then also for the the breed for the first two benchmarks, it was not controlling the PD coefficients, but for OGAS, both the breed and OGAS, they were doing that. And I think that's also very interesting because, for example, if you have this Navier-Stokes and you choose the viscosity as a part of the pre-training, you don't want to have, maybe it's uniform. You can, of course, guess to try, oh, let's do it like logarithmic or like some proportional too, because you just understand. But maybe for some systems, it's not so obvious, which should be the really good prior. And so then the model can find it itself. And then also, if you have, so when you have different PDEs, you would have different needed coefficients for every PDE. And so you have like this heterogeneity. And then also it's possible that every PDE system, the solver runs for different time. So you could try also to do active learning on like, or you also impose this, what's the cost of generating the data, or like what's the time and etc. I think there's, I mean, for, let's say, I think the first thing to try, the first thing I would try for adapting OGAS or breed probably not, but OGAS to this case for foundation models is like try to take different PDEs and to try to have this mechanism to choose between the PDEs. And this is already probably interesting if it can do this automatically. And then also if you start to add and these parameters and these initial condition parameters and initial condition types, so you have a lot of like degrees of freedom, which of course you can try to find yourself, but with active learning, maybe you can do it like more automatic indeed. And then for the downstream task, well, I mean, you can, for example, if you pre-train on the synthetic data and then you downstream on synthetic data again, but just for some harder system or for different, of course, task, then you can also try to choose the data there. I mean, why not? I think that's a good idea since you have this choice of whatever data to create. And then if it's observation data, maybe it's also like you can combine for both sides. I mean, for observation data, if it's like not labeled, like just the usual task, or maybe how often it should be shown in the training, like more of an adaptive sampling and like in the more usual sense of training the neural networks. So I think that's how I see it at least.
Okay, thanks. I'm done. Thank you.
Thank you.
Thank you very much, Mathias. Okay, so the next examiner is Kyle.
Okay, hi, Sofya. Thank you very much and congratulations again. As previously said, I mean, I think the presentation was great. I also found your thesis to be like very well written and well organized, and just also was impressed with how the different sections build on each other, and it tells a kind of uh, coherent and very thoughtful story. So that's not always the case. Sometimes they're a bit more meandering. So congratulations on all of that. Um, so I have maybe two or three questions. So the first one is that in the thesis and in the discussion and the discussion about the kind of exploration exploitation trade-off, the exploration, you're often referring to like a uniform distribution, and there's some comments in your thesis about you know about the uniform distribution itself. And I guess I'm just thinking that one thing about the uniform distribution, especially in the sort of Bayesian statistics setting, is it's not really very well defined, in the sense that if you change the parameters of your system, it's no longer going to be a uniform distribution. So it's in that sense, it's like not parameterization invariant. So you're sensitive to the choices of how you parameterize your system in the first place. And so I'm just curious a little bit about how you think about that. And so there are other approaches that are somewhat more kind of natural, or kind of uniquely defined notions of something like a uniform, that come from things like, I don't know if you're familiar with things like Jeffreys prior or reference priors, but they tend to be based on some kind of information theoretic ideas. And the problem there is that they're very expensive to calculate. So, but they do capture things that you talked about in the presentation and in your thesis, where if you just do naive uniform sampling, you can have big regions of parameter space with kind of trivial solutions, or nothing really changes. And these kinds of more information theoretic notions of priors, capture that, and they would sort of put a small volume associated to regions of parameters that don't change much.
Yeah.
I'm just curious how much you thought about that kind of that issue, since it comes up a lot in your thesis, and then if you had thoughts about sort of the trade-off between something that I'd say is sort of naive and simple and fast with the uniform, to something that's more principled but very expensive and maybe not very practical. And if you thought about also, like, if there may be algorithmic approaches that would allow you to somehow, interpolate between them, or just generally that topic. Any thoughts that you have on that?
Thank you for the, oh my God, not the questions. What was in start? I'm starting to melt. I think I'm writing the sand, so I'm trying to escape it. So yes, for your nice words, I appreciate it very much. So about the question, I did not know about other prize, the Jeffrey and another one. Let's say, was not too much concentrating on trying to choose something else. But what I was thinking about is that I even have a post note somewhere in my office, like saying, "Oh, what if we could, instead of doing the uniform for the exploration, we could have like a negative of what we have learned already about the hard samples, or like to have some kind of a model of what we actually explored, and try to have not just uniform, but uniform and not seen yet, like kind of try to have like, importance weight, but the other way around. So like try to see exploration from this kind of side. But I did not think about others aside
Yeah.
from these. But
No,
I think
that's fine. Yeah, I guess, I mean, if I mean, I think they are interesting, but I guess maybe more generally is that maybe you could still say, thoughts about the trade-off between trying to come up with somehow like a smarter, a smarter type of prior that might have more computation, but at some point you're going to be paying for that as well, and it's not necessarily going to help you. So I don't know, just thoughts about how you would approach that kind of trade-off.
I mean, if it is complexity over the parameter space, and if we want to go for, well, for geometry, for sure it will be large. Or if, as Ronan was asking about the initial condition states, and then we want, if it is, let's say, at what point is it indeed too much of a work to have this exploration that is not uniform distribution, which is easy to sample, but maybe let me just think for a moment, because it's a very interesting question, and I, let's say, never really concentrated on how to do exploration otherwise, but because yeah.
I mean, it's okay. It was just kind of
I think
just
I
curious
can't
about your,
generate, I
yeah,
cannot
yeah.
synthesize anything that is like right now in my head about that. But because again, I don't know what is, for example, the complexity of these more sophisticated exploration priors. Like if it is, I don't know, log n or n log n, I mean, something like this, maybe it's okay. But then I don't know. I mean, I just generally don't know what's, let's say, again, from with the OGAS, I think it's possible to have the exploration by trying to have the prior differently, not only like if you associate easier, let's say not even easier samples, but like other samples, just like because you, or maybe you can try to put some other criteria into training or learning to make it a bit more random or like increase, something like this. But yeah, I can't give you more than that, I think. I would love
Okay.
to think about it.
Sure, that's
Because I
fine.
have all the
It was
way.
pretty open-ended. I
Yeah.
guess another question I was wondering is if so when you're doing the active learning, you're primarily searching over, either initial conditions or parameter space of, the like of the systems themselves. And I'm just curious if you looked much into trying to sort of sample or optimize over other kinds of things, so that might, for instance, be hyperparameters in the learning algorithms, or maybe hyperparameters in the solvers themselves. And I guess if you start to mess with the solvers themselves, it
Hmm.
gets a little bit into things like um, uh, what's the word, multi-fidelity type optimizations, where maybe you have some forward solvers that are very fast and you learn something, but they're not perfect. Did you explore that direction much, or do you have any thoughts about that direction, or how you would maybe need to change the algorithms you have to address those situations?
So there is the multi-fidelity active learning for neural operators paper where they basically do this choosing the resolution training, which I think is kind of going into this direction more. And then there
Mhm.
is also the work where it's the active learning of the solution state time step itself. So like let's say, but it's a bit more complex. Let's say I think it's going into a bit different direction. It's more about like, oh, do I get the next state with the solver, or do I get it with my maybe well-learned surrogate, or like do I just stop there? So maybe there is also the way like to to think about these directions, but in my thesis, let's say I didn't do anything but the initial parameters or the system parameter, the PD parameters, or like those, for example, the size of the domain. Let's say it's still the system itself, more like it's just. But the size of the domain is also, in a way, if you're keeping the resolution, if you change the domain size, it's in a way starting to be kind of a multi fidelity in a way. So maybe that's kind of going a bit into this direction, because it's not part of the coefficient of the PD system itself, and neither its initial parameter itself, but something else. So that's
Right.
what was else done for the domain size, because for example the Kuromoto-Sivashinsky, it's more sensitive to the size of the domain. It starts to get very different as the domain size differs. So basically that's where I guess it gets there. And but what I would have tried, or how I see that, I mean, yeah, I guess the maybe would be interesting is like to somehow know with which time step, sub-step at least, to get the data from the solver, maybe. Like instead of having, like you have some the solver times discretization resolution, so the delta t. And of course, you need depends again on the solver, but for some it should be some at least that to satisfy the I forgot the word, but the criteria so that it's actually not getting to break the solver itself. I forgot. And so maybe, but usually what is done is like to have this sub-stepping when you're, okay, you don't send every step to the neural network, but every like fifth or 10th. And maybe that's also interesting where it can be trying to choose like, oh, maybe don't send me every one, but maybe start to send more as it progresses in time. I think that's maybe something also interesting, like, because maybe you could control also the solver, but I guess, yeah, as you said, like if you start to mess up with the solver, maybe it will give you like errors or non values, and then you just start to break that. But if there is some way to catch that also, then maybe it's okay. And about the surrogate itself training, I think it's more about the hyperparameter optimization, like when it's I never really looked into this area itself, but I think that's also something interesting that can be done maybe in Melissa, is like not the active learning per se, but because active learning in the end is more about which data to create, not like the surrogate, but I guess that can also be done online maybe. So, but yeah.
Yeah. Okay. Great. And then maybe just one other one, and if you don't have to. It's also kind of open-ended, so if you don't have
that's the
any
most
particular
interesting, right? I mean,
yeah. No, but I liked your point at the end where you were talking about, at what point does the active learning problem become kind of harder than the learning itself? And was thinking about that while reading your thesis, and I was just, I guess, when you have this sort of static pre-training, compared to the active learning, you can start to think of the active learning algorithm and the training and all of this together itself is somewhat of a dynamical system. And things like mode collapse or different types of dynamics that you're running into. And I guess I'm just wondering if you have any, intuition or thoughts about if you see it as sort of maybe useful to actually see the active learning loop as actually a dynamical system itself, and either from like a theoretical point of view that there might be some insights there, or from a practical point of view. And if you don't see anything, that's fine. I'm just curious if you have any thoughts on that.
I do have thoughts on that. I think this is something that actually makes it the harder problem than some others, which you see in like design of experiments, Bayesian optimization. Like, yes, it's like the black box, the solver, and in a way, not necessarily black box, the neural network, but let's say it's let's say you don't have a fixed target. You want to, in the end, like even the uncertainty, it's say, even in the simulation-based inference or like inference in general, you have this like, okay, my system is just there and it's fixed, like, I don't know, our system or something. And then, I'm trying to get the inverse solved. But here I'm inversing something that's like constantly changing. And also, it's not just changing, but it's changing in a way slowly. So it's like not completely crazy system, which is like, oh, now I'm this, now I'm that. No, in the end, the weights are moving more or less. They're quite close to each other, let's say. And so I've seen at some point at some point I was getting crazy about different methods of optimization. There's some, I forgot the word, CE methods, cross entropy methods maybe, but and there was also some simulated annealing, or like there is some I forgot the word again, but there it was something that you have let's say you have the final distribution, and then instead of trying to directly try to approximate the final one, you first approximate just like the linear combination from like some uniform. And so it's kind of a growing number of growing number or not growing down, growing system. And so, but in this sense, you're building this growing distribution yourself. But in case of neural networks, it seems like there is maybe some kind of final state of uncertainty, which is like the hardest one. And then it's kind of growing to it. Let's say there is some path to maybe it can be somehow seen from this area. So there's also, I think I've seen some papers and some research, but not too much about the Bayesian optimization for moving target, but it didn't go too much because, like, let's say it's not only that the neural network moves as what you're trying to basically inverse, but it's also affecting it. So it's like it's just so complex. Like, yeah, indeed, like because of this online and you don't have this like really fixed like, and also you are part of the when do you want to fix something, like, or how often do you resample, or like there is just so many of these little things, little knobs to change. So
Sure.
but
Yeah,
I think there is something interesting to look, but it's definitely like very hard task because of this non-stationary target.
Yeah.
But
No, agreed. Yeah, it definitely doesn't sound easy to analyze, but
and that's
okay,
why
well,
probably
yeah,
I'm mostly
yeah,
doing some empirical stuff because, well, at least some understanding of how it works
yeah.
before trying to put some theory on it.
Okay.
Hopefully.
Well, thank you very much. Yeah, I mean, I had other questions, but they were, I think, mainly addressed already. So again, yeah. So thank you very much, and congratulations on the nice thesis.
Thank you. Thank you.
Thank you, Kai. Okay, so perhaps I can make a few comments
Yeah,
before
sure.
taking the final word to Bruno. I would like to congratulate you also for your presentation that I really appreciated. It was really clear and really pleasant to follow. I'm clearly not a specialist of neural networks, so I had a few stupid questions.
Not
probably,
and no questions
yeah,
can be stupid.
They were really stupid.
Okay.
I
If you say so.
a few ones that probably were less stupid, but both Ronan and Mathias and Kyle talked about this in theoretical results and multi-fidelity aspects, etc., etc. So I won't discuss this again. So just perhaps a few comments. I really enjoyed what you said at the very end about your open question. I really agree with what you said there. When Matthias discussed in the first part of his questions, it made me think about a link. Probably, yeah, there's probably links with what's called adaptive mesh refinement in numerical simulation.
I think it does. I mean,
when you're looking to new collocation points,
yeah, especially for pins, it's definitely.
Yeah,
and that's why I said the geometry aware. You can also like change the points. So
exactly.
Maybe,
so there's an enormous scientific literature that was done on this subject probably 2 or 3 decades ago. It was very popular at that time, and with the ratios that were adapted to the application. For example, in fluid mechanics, many criteria that were really adapted to, for example, the level of turbulence, etc., etc. You know where to put your collocation point. So perhaps there are some ideas there, and regarding what Ronan said about ocean application and climate application.
It's more closer to.
I think it's so. Well, first about the generation of the initial condition. I can mention that there was a PhD thesis probably 2 or 3 years ago at Météo France, just on this specific point of generating automatically initial condition to make the ensemble. And I think it was by Camille Bézon, but perhaps I'm wrong, but I think it was him. And typically he proved that their model was of the order, the size of the state variable was of the order of 10 to the 8 or 10 to
Okay.
the 9.
Yeah.
And actually, the latent space that was really relevant for regenerating initial condition was only of dimension 30 or 32 or something like that. So it seemed that it was really efficient. So it can work. It seems that it can work.
Yeah.
And more generally, for if you want to learn, not only generate initial condition, but learn something about the climate model or ocean application, and since the dimension are so huge and the simulation results are so rich, and the simulation by itself is so expensive, that it's probably a pity to throw it away.
Yeah, this is a very
just to focus on one or two quantity of interest, because dozens of quantity of interest. And if you have to redo the simulation just because you have forgot to look at one quantity of interest, it's a pity. So I'm not sure it's really relevant to do online learning for this, but I'm pretty sure it's really relevant for process studies where models are more simple with less degrees of freedom and a few parameters that are really clearly identified and that drives the process. And probably also for other types of model, Ronan, perhaps you will agree with models, like ocean biogeochemistry. This is a set of a few tens of ordinary differential equation with a few tens of parameters. And typically, and the cost of one simulation is of the order, let's say 1 minute, and probably it's possible to.
Yeah, I think it's let's say for the online training, there is this. So let's say you either not that you accept, but let's say for some application it will work because you kind of need probably to have better understanding of the amortized cost, like if you do learn the surrogate to in the end provide what the solver does, then if you spend all this time, but then it's like giving the solution significantly faster. But if you manage to like really make it learn accurately, then maybe the amortized cost of generating then also throwing, let's say I wouldn't probably throw something that takes weeks of generation. But then I think this is where the online probably fails, or at least it needs at the state it is right now, where we do it just throw them, let's say, because we are not working indeed with like days of computational cost. But I was thinking also about like maybe there is some way where you have like additional client which is saving the data, I don't know, but like it's disconnected from the training, so at least it's like the training is still in situ, like you don't store, you don't have this IO overhead, etc. Like it still continues to do what it needs, but then maybe some of them needs to be saved and maybe some don't need to be saved, and maybe you can try also to do this and like to at least indeed have like some data while you create it, maybe it can be reused, or there is probably a lot of things that can be done for this case. It's just,
I agree.
Yep.
Okay, so again, congratulations on the final work to Bruno.
Thank you very much.
Thank you.
So I'm not going to make any questions. We discussed for 4 years.
For 4 years of questions, yeah. But I love talking to you.
But first I want to congratulate you for the presentation. It was very good presentations. And then, as usual, a PhD is an adventure, a human and a scientific adventure, and your PhD was an adventure, a scientific and a human one. I have one. Things were not easy for you, and it was not your fault. I remember you took the plane from Moscow to here the day the war in Ukraine started. And then the first month you were around, you were not fully available mentally to discover a new culture, a new country, make new friends, discover your subjects. You were worried that your friends were, some escaping the country, not to be drafted for military services.
I took a lot of toilet breaks to cry, yes.
I remember. So this makes things very difficult for you from that point of view. Scientifically as well, me on my side, I'm an HPC guy. I mean, I have been in neural network for some years now. I did study my PhD actually on neural networks, but it was a long time ago.
Probably.
And basically we had Melissa with online training, something, and this idea, I mean, a PhD subject is something where basically you have kind of an idea, but you obviously don't know the where to go. Say, oh yeah, something like active learning could be something interesting to explore, and you apply to that positions, and your background was math, basically. No computer.
Not computer science.
No computer.
That is
no
not,
HPC
yeah,
for
not
sure.
HPC for sure. I remember I even wrote you, I think, in the email like, I maybe did like PyTorch 2 GPUs. That's all. It was not much understanding what is client.
Remember, you sent me your master thesis. I opened it. And it was full of math. You say, well, I should be serious. I don't understand anything.
It was actually about the image refinement.
Yeah, okay. That was
a little bit.
that was a bet basically to say, someone with a strong mathematical background in NQ, if you're willing to spend the time to work with supercomputer, then as I usually say, a supercomputer is like a Formula One. I mean, it goes super fast, but most of the time it's in the garage and you have to fix it. So most of the time you're trying to fix where it never works. And so you accepted the challenge and you say, yeah, why not trying to be there? I'm ready to jump into that. And things worked out quite well. I mean, we did all this, for no active learning in Melissa went through all these steps to this final one was, I mean, I progressed a lot on understanding all these issues, all this complicated stuff and putting everything together and not making simple active learning, as you just said, but active learning in this online context where everything is moving at the same time. And I'm very happy with the results. I learned a lot. I hope you learned a lot. I'm quite sure you progressed a lot. And on top of that, and I will stress that it's also a team adventure because you need the development of the system. You need these experiments. You need to access this supercomputer. You need the theoretical parts. You need a little bit of understanding, etc. Read this paper. I mean, this AI world is crazy. There is a new paper every week on the topic almost. And so
I mean, I get the email about new papers every day.
So it's very challenging to work in that domain, and you succeeded. You were stressed with the help of the other people. I mean, we really worked as a team, and it was really interesting to work that way.
I don't know if Abhishek is online somewhere. I know that he's in India. There is also Pierre.
Yeah. And Emil and the others that went in the team. And the last thing I say is that you were incredible. I mean, after a couple of months, you knew everybody in the building. I mean, more than me. We went to ICML in Vienna, and I had the impression, I mean, after like a couple of hours, you really set up a meetup point about AI for science. And you
made a picture with Kyle.
You see, you met Kyle. So you're incredible. You have this capability of establishing contact with many people that is quite impressive. Okay, I will conclude that. I was very happy to have these 4 years with you working with us. It was a very nice time. Thank you.
Thank you.
Thank you, Bruno. So it's time for the jury to make his decision.
So everyone...
Yeah, probably we will stay here, Bruno.
Yeah, we stay here. We ask everybody to go out for maybe 15, 20 minutes.
15, 20
and we ask you to come back.
I leave. So you need to make the breakout room, right?
Yeah.
So we're going to create the breakout room for the jury. So you will be invited to join the breakout room. So please join the breakout room. Oh, no, you can assign them. Okay. Perfect.
Go, doctor. Sorry.
Sorry, I did my interview.
Can you talk to...
And me, Sofya, can you put myself?
So...
Perfect.
Ronan there. Do you need... That's all? That's all?
Yes, that's all.
And then... because this computer will...
Leave it on. Just, put yourself in the waiting room.
That's what I'm thinking. I guess it could be... I don't know. Okay, I don't. Maybe I will be myself. I don't know.
Passe par ton micro, du coup.
Or this one, on peut laisser.
Or the computer which is controlling this. It's which one is it? But what is the account?
Louis Boulanger, je pense.
So I can add Louis then.
Okay.
And then I can just Okay. And what is I think you should just
Good. Oh yeah, we have received the invitation, Sofya.
I pause recording, I guess.
Yeah.
I don't. Okay. Yeah.
Is here.
And my
Okay,
camera
think
is
so.
hammering. Sorry, I think.
Yeah. Okay. Okay, Sofya, so the rules. So I will make just an overall report what we just said in our discussion, and that the final written report will be finished at the end of the week, just iterating the email. But yes, the jury was very happy with your oral presentation, which we found very clear and pleasant to follow. You gave a good synthesis of the work that was done during your PhD, and good choices to present it, which is fully coherent with what we've done with your manuscript. That was also very well written and organized. So we would like to emphasize the fact that well, this was a really timely scientific topic of active learning for physical models, and in this context, you made a thorough work, a logical, coherent progression with relevant experimental settings, relevant numerical experiment, etc., etc. And doing this, you obtain significant contributions to online active learning for deep neural network. Of course, providing this new sampling algorithm and demonstrating its efficiency. So for physics-informed neural network, with your contribution to adaptive and online learning with Gaussian mixture, to adaptive diffusion, adaptivity for diffusion with diffusion models also. And succeeding in making a clear comparison. This is somewhat messy, but you succeeded in making a clear comparison with a state-of-the-art method. So congratulations for this. We also emphasize the fact that this was done within a complex technical context. It's high-performance computing. It's Formula One. The integration within the Melissa software was also challenging, and well, you had to make Melissa, you had to make additional development into Melissa to integrate your work in it and drive this integration. And finally, regarding the question session, well, you answered many questions on quite different aspects of your work, and you looked very comfortable answering these questions. And clearly, you became a specialist of your domain, and well, you clearly mastered the topic. So for all these reasons, the jury is happy. Yes, the title of Doctor of the Université Grenoble Alpes. Congratulations.
My God, they are crying. Of course. Oh my God. at what time I need to read the
Oh, yeah.
thingy or forgot? Oh no, it's written in there. Yes, I've seen it.
Yeah, I forgot also.
I just don't know if I should do this first or
Yeah.
if I can do first acknowledgement.
You need to do this.
I don't know at what point I need to do this. That's why.
If you want, you're not obliged, but if you want.
In what sorry? Not obliged.
Yeah, you're not obliged.
To read it?
Yeah.
No, I will not be able to say that. It's so weird. Well, in the presence of my peers, my friends, and my family somewhere online, hopefully. So many friends. With the complete available. I'm sorry. With the completion of my doctorate. I'm sorry, I think I'm just having a emotional crisis or something. You know I'm emotional, so okay. I need my water.
Yeah.
I'm sorry if we make you all wait. Well, 4 years. What 4 years? With completion of my doctorate in computer science, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, in my methods and in my results. Usually now. That is the end of the end of the text. So it's official that I'm accepting all of these things I need to be doing as a now Dr. Dymchenko. My God, so when I was preparing for this defense, I thought that I will have time to prepare my acknowledgement list, the whole speech of this, but in the end I have to just wing it. But well, it was such a journey, my God. But I'm very, like as you said, Bruno, it was just kind of a gamble. But honestly, the moment I talked to you, when we had our first meeting online, it was just, I knew that whatever I will be doing with someone who's friendly, just nice personally. So it really played a huge role. It played a huge role over these 4 years. I don't think I would be doing it for so long, an additional year, if it wouldn't be you. I mean, it was always a pleasure to talk about life, about work, about anything, and just be open about whatever I feel and how hard it was doing is all because of my ADHD and just in general the post-war, not post-war, but okay, post when I arrived, all of these in general, all the changes that come with not just doing PhD but emigrating and doing PhD. It's like it's just I'm a different person completely from 4 years ago. But a huge thank you for you just be you. And supervising me, I really liked the growth we had both, like just learning from each other, really liked it. But then, of course, thank you for all my friends who are supporting just my crazy mind with all of this, with my not very social, but also invert, and I forgot, oh my God, extrovert, introvert, just two modalities where I'm, oh yes, let's meet, but then I'm not meeting, and I just like, but I just appreciate that some of you in the end came and just being here, being with me. The new friends that I get during these 4 years, and just, oh my God, there's just so many people, like there is thing which I had as an idea for my speech. Usually there is, at least in Russia, saying that to grow a child, you need a village. You need so many people than just mom. And this PhD is my baby, and it took so many people to really just make it born today. So I'm just thank you for everyone. This, thank you, Kantan, for everything. I don't know. I don't think I would do it without you either. It was so hard. I'm just so happy that you were me for all of this. And then I'm not sure. I don't know if my mom or my family is online. Can somehow someone turn on their maybe mic to understand if it's not or not? Because I just wanted to say in Russian, but I don't know if they're here, so I don't think I see them. But anyway, спасибо, мама. Спасибо, моя семья, и спасибо, мои друзья из России. Конечно, Настя, спасибо, что приехал. И другие люди, это вообще община, как бы вообще все, это очень тяжело. Смайлику спасибо огромное. Не знаю, сколько вы там тоже меня перетерпели. Все поддерживали всегда. Очень большое спасибо Смайлику, вообще самые мои друзьяшки. Вот, и в целом Греноблю со всей русской комьюнити, Кириллу, за всей помощью и так далее. Вот. It's very emotional to get not just higher education for not the first in family, but let's say first doctor for sure. And it's such a weird thing because I don't know, I just was always trying to be the best. I don't know what for, but in the end, it's like the most interesting path in the end. And I'm very glad that I decided to do this all, and that I decided not to quit as I thought during the second year when I took 1 month of vacation. It was very helpful. So if anyone here doing PhD or planning to do PhD and you think that you want to quit, that's absolutely normal. That is like, if you don't think about it, that's not normal at all. This is the thing that you as a scientist, you need to be always having some doubts about everything. Otherwise, you're trying to explore the world, exploring the research, the science, all of this. We have doubts all the time, but in the end, it's paying off. And yes, I'm glad that it's all just brought something actually new and nice, and that's probably all. Thank you, Joris. Sorry, I forgot. Thank you, Joris, so much for all your nice compliments, for your questions, for your time, for just us saying yes to be part of this day. And thank you, reviewers, for reading this heavy manuscript, which I did enjoy writing it more than papers because you have all the place in the manuscript you want to write anything like for long and not just 5 pages. So it was also, yes, the Tamov team in general, of course. I mean, Annie, she was here, but she went somewhere. But Annie also huge part of everything to be working as intended. These little and big things. Thank you. That would be all. It's Dr. Dymchenko! Yay! Peace.
We can maybe free the people and the jury.
Yes. Thank you. The camera doesn't see me. No, camera.
Thank you very much. And congratulations again. And yeah,
Thank
all
you,
the best.
guys. Thank you, Mathias. Thank you, Ronan, for being there very much.
Congratulations.
Congrats.
Thank you for accommodating my time zones.
All right. See you.
Okay. So hopefully the food is. What's the status of the food? Not fooding? Yeah. Well, we can definitely close.